So as an exercise, show that the function phi, mapping the integers onto the set of integers modulo n, defined by phi of a is equal to a modulo n, is a homomorphism but is not an isomorphism. And as a second exercise, let n be a given integer, and let the set, which we denote n times z, be the set of all multiples n times a, where a is an integer. That is, the set of all integer multiples of a given integer n. Show that the function phi, mapping the integers onto this set, the integer multiples of a given integer n, is defined by phi of a, that's equal to n times a, is an isomorphism. So recall that a Cn axis is a symmetry element if and only if rotation about this axis by 360 degrees divided by n produces an identical molecule Similarly, a mirror plane is a symmetry element. If and only if reflection through this plane produces an identical molecule. Now, mirror planes are designated as follows. A molecule may possess, or will possess, a vertical mirror plane, which we denote sigma sub v, that is parallel to the principal axis of symmetry, a plane which we denote sigma sub d, and we call this a dihedral plane. That is parallel to the principal axis of symmetry. And bisects two C2 axes. And finally, what we call a horizontal plane, which we denote sigma sub h. That is perpendicular to the principal axis of symmetry. So let's look at some examples. Start with the water molecule. And recall that the water molecule has a C2 axis passing through the oxygen atom, and that the water molecule has a two-dimensional geometry, and so the plane of the molecule itself is a mirror plane. And we also have a mirror plane that is parallel to the principal axis of symmetry, that is perpendicular to the plane of the molecule. And so we have two vertical planes. We have the plane of the molecule itself, and we have the plane that is perpendicular to the plane of the molecule. Now, by convention, the z-axis is chosen as the axis of highest rotational symmetry. That is, the z-axis is chosen as the principal axis of symmetry for the molecule. So again, let's look at the water molecule. We choose for the z-axis to coincide with the C2 axis of the molecule, and we can choose for this to be the x-axis, so that the y-axis is perpendicular to the plane of the molecule with the positive direction going into the plane. And so we can identify two vertical planes. We have the plane of the molecule, which is the xz plane, and we have the plane that is perpendicular to this plane passing through the oxygen atom, and that is the yz plane. So now let's look at the carbon dioxide molecule. We have a C2 axis passing through the carbon atom, and we also have a C infinity axis which contains the molecule. And so once again, choosing the z-axis to coincide with the principal axis of symmetry, the z-axis will be the C infinity axis. We can choose for this to be the x-axis. So once again, the y-axis is perpendicular to the axis, the plane of the molecule, and with the positive direction going into the plane. So notice that there are infinitely many vertical planes, vertical mirror planes, including the XZ plane and the YZ plane. Now notice that this molecule also has a horizontal mirror plane. We have a mirror plane that is perpendicular to the principal axis of symmetry and contains the C2 axis. And so, once again, one horizontal mirror plane, which coincides with the XY plane. Also notice that in order for a molecule to possess a horizontal mirror plane, it must have an axis of symmetry that is perpendicular to the principal axis of symmetry, as in the case where the C2 axis is perpendicular to the C infinity axis. So now let's look at the xenon tetrafluoride molecule. Now we have a C4 axis as the principal axis of symmetry. And so far, we have identified two C2 axes. And these axes each contain two fluoride atoms and the xenon atom. So once again, identifying the z-axis as the principal axis of symmetry, which is the C4 axis. We can identify one of the C2 axes as the x-axis and the other as the y-axis. So notice that we have two vertical mirror planes that coincide with the two C2 axes that we have identified so far. So we have a vertical mirror plane that coincides with the XZ axis. We have a vertical mirror plane that coincides with the YZ axis. And we also have the plane of the molecule itself, which is perpendicular to the principal axis of symmetry. And this coincides with the XY plane. So let's look at the molecule in the XY plane, the plane of the molecule. Notice that we have two mirror planes that bisect two C2 axes and is parallel with the principal axis of symmetry. And we will denote these sigma sub d and sigma sub d prime. So notice that the intersection of the horizontal plane, the plane of the molecule, the xy plane, with the plane sigma sub d, and the intersection of the horizontal plane, the xy plane, with the dihedral plane sigma sub d prime, are two additional C2 axes of the molecule. So now let's look at a molecule of ammonia. Notice that ammonia has a C3 axis, and that the plane which contains the principal axis and any one of the hydrogens is a vertical plane. So let's look at a top view of the ammonia molecule. Where the three hydrogens are in the same plane, and the nitrogen atom is above the plane. Then we have three vertical planes, which we will denote sigma sub v, sigma sub v prime, and sigma sub v double prime. So let's choose for one of the hydrogen atoms to coincide, or one of the hydrogen-nitrogen bonds to coincide with the x-axis. Then we have one vertical plane that coincides with the xz plane. So as an exercise, identify the mirror planes in a methane molecule. Okay, so we'll end here for today. Next time we will continue to look at the symmetries of molecules, and in fact, the majority of the next lecture will be devoted to point groups and their applications. So I hope you have enjoyed the 5th lecture. Thanks for watching.